I think most of you have seen me already. In case you haven't met me, I'm Max, CEO and co-founder at DGG. Happy to host this event. And my background originally is from computer science, graphics, media studies, and I went to Fraunhofer to work there, did my PhD very close to this building, founded DGG 5 years ago, and really happy to be here with you. And what I want to talk about in this presentation is something that we call RapidPBR, which is a product extension to RapidCompact, and I would love to basically continue where Janos already left off. So just have a nice transition from that presentation and staying a bit with this topic of content pipelines, content optimization, and specifically looking from this angle of CGI content and bringing that to real-time experiences, what we have also seen in the previous one. So, as you might have seen, AR is something that is becoming more and more commonplace in e-commerce today, right? Here's an example that Shopify created a while ago where they have these two baby strollers. One is the real one, the other one is augmented, and you can't really tell the difference. It's actually at a level where it practically works very well and works in everyday life applications, but the problem is the content. So what we're looking for is we have these applications, but how do we get millions of 3D assets into those? Because there are thousands of products and variants at thousands of companies worldwide, and it makes millions of assets that we would need to create to enable this at a really large scale. And if you know DGG, you might have heard about RapidCompact, so really just some context, what are we talking about there? So RapidCompact is a tool that can handle a 3D asset and bring it into all kinds of applications, right? Doing things starting with rendering thumbnails, optimizing the mesh, reducing draw calls, baking materials, and so on, compression, and then getting it into a certain application and doing whatever is necessary to have an optimal representation for that application. So maybe for a floor planner, you have something, if you take this asset where you maybe cannot open the drawers, and then you can automatically cull all the interior, and that's one optimized version. And maybe you have another version that's more detailed and animated, and you can see inside the drawers, then you cannot cull them, right? So depending on what it is, it creates the matching variants, and you can configure it and run it at big scale. But what we discovered at some point is hey, this problem is really deep, and we love deep problems. We have a research background originally, but in practice, many people don't even get there because they're lacking their 3D models, right? So to get real-time 3D assets, I need non-real-time 3D assets first, and then I can take that base model, right, as Janos showed, and get it into that application and optimize it down, but I need a high-quality source. And there are many ways how to get there. And I want to talk about just one of them, but I acknowledge that there are many ways. And so getting models created reliably as a service is one of them, right? And we heard about that in the presentation from RenderDad, so that's really cool. And the folks from CG Trader have figured out as well a very scalable 3D asset production pipeline over years. So those are just two companies who are working on this, and there are others out there that are trying to do the same. So getting models created reliably at scale as a service, and we also heard other presentations, like the one from Fibble, right, where they took that challenge and said, can we produce 100 models in 3 days? Yes. And there, 3D scanning helped a lot, right? So the combination of some methods, or sometimes maybe even 3D scanning itself, can be quite promising. That was also our first talk, nerves, kind of related to that. Finally, there's also the approach to take CAD data, and tomorrow we'll have a presentation from Visometry where we hear how they use CAD models to do things like AR-based support for after sales, repair manuals and so on. So taking the original data that is there, and there's this quote from Carol Bartz from Autodesk saying look around you, if it wasn't created by God, it was probably created in AutoCAD. And I think this probably applies to this microphone here, probably to this laptop and so on. So yes, there are 3D models and we can use them, right? And that has an advantage. But then maybe not every model is available in CAD with all the materials and all the information that I need to generate a photorealistic representation, which is different from doing a repair manual, right? So that's similar to what we have seen in the presentation about the pipeline at OBI. And if we can build somehow a database of CGI content, then we could use that as a source to feed data into our real-time apps. And I took data from IKEA here because they're very advanced and there's a lot of public information there that I could easily Google and grab. But if you look at this picture here, on the upper left-hand side on the upper right, then it's very clear that this is a CGI rendering where they slice through this model to just show how the upholstered part of this iconic armchair is looking inside. So that data is somehow available in CGI. It's used like to create like these product shots here for the catalog, and it's easy to customize it for many different scenarios, exchange materials, adapt it to different geographies, like the legendary IKEA catalog is available everywhere around the world, but everywhere it looks slightly, like a little bit different, right? Adapting to the local like habits and how people's flats look, etc. So this configurability was very important for them. And many others have these models, often using formats like V-Ray scenes, right, and 3ds Max, or maybe other renderers, other DCC tools, maybe Blender scenes. So what we asked ourselves was, can we somehow leverage that data to create real-time ready assets out of that fully automatically? And Obi has done it the same way, right? Like taking these V-Ray scenes, creating in that case a modeling standard. And we went a step further in the sense that we don't always have control, right, over how people create assets, because like we are dealing with data from many different vendors, and so we can't just enforce a standard. We contributed to one with the Chronos guidelines. That is one thing, but it's not talking about V-Ray either. And what people use for their renderer, ideally we would love to say, just bring what you have and we'll make it real-time ready, right? So that's the idea of RapidPBR. So it's a fully automated tool that does this translation, and saves artists and uses time in that sense, and just allows you to bring your DCC data that was originally not even created with real-time in mind, but for CGI. And the pipeline looks like this. Right now, we're supporting 3ds Max and V-Ray because we just figured out, hey, this is by far the most popular pipeline that people use there. RapidPBR then converts to another 3ds Max file with a different material model that can also then be directly exported to GLTF, and then we can take Rapid Compact, take it from there, and bring it into all kinds of further applications. And we're thinking about adding Blender support next. There are a lot of other DCC renderer combinations that we could support. And for now, I just want to give a little insight into how we approach the overall problem. So going a divide and conquer way, first of all, we acknowledge that there are different kinds of materials that you can classify, right? And like some materials are basically just consisting of a set of parameters. So if I have glass or some like polished metal here, then I don't even need a texture, no texture maps of any kind, just some material properties, and of course they need to match. So what I have in the real-time version needs to match what I have in the offline CGI version. But apart from that, they are rather simple, so that's level 1 of materials. And level 2 is then materials that are textured. With or without tiling, and yeah, like everything that's basically textures that are non-procedural. So they consist of pixels, and that's what I get. And I can take that and then somehow translate that into something that I can use in real time. And the most tricky part is having procedural materials. So procedural materials like basically an algorithmic mathematical description somehow that goes into some algorithm and then generates a cloud or a wood pattern, which is pretty cool in offline rendering because it basically gives you infinite resolution and you can always tweak it and it's easily configurable and so on. But in real-time rendering pipelines, that usually doesn't work like that. So usually these models are not easily like renderable in like a GLTF version, for example. So that's something that the industry is working on, and I think we'll talk about that maybe tomorrow, even during the panel discussion. So procedural materials is like the next level, and that's why it's level 3 here. And we just acknowledge that these different kinds of complexity classes exist. And that allows us later on to basically say, okay, we found a simple solution to handling procedural materials now, but maybe in the future we can come up with something better that allows us to preserve this quality in real time. And for now, we're supporting different input materials. We have just listed here some examples from like the V-Ray nodes that we can convert right now. For the sake of time, I'll just skip over that, but also saying there are not only material nodes, but also geometry nodes that can be quite challenging. So if you remember the pictures of the beaver, it had this fur. So if the beaver is rendered in V-Ray and has this fur on it, it's usually quite hard to translate that, right? Often they're using particle systems or something like this to model it, and that cannot easily be transferred into real time. So that's always a problem. But then there are others that we can somehow bake down basically and generate a real-time version that somehow works. So another thing that we looked into then in the context of the materials, which is what this pipeline is all about ultimately, is supporting different extensions in the GLTF model in order to enable different effects. For example, the transmission and volume. So here's this chess model, and you can see that these chess figures have some of them, like the pawns, have these little heads are made out of glass. So there we have the transmission volume IOR extensions that allow us to get this effect in real time. And we recognize this in the V-Ray input nodes, recognize this material somehow should look like this kind of glass, and then we try to read the parameters, translate them, and ultimately come up with something that has these extensions attached so that we can reproduce this effect in a GLTF material. And there are others like iridescence that are planned for future support. Like if you think about the olive dish GLTF model, something like that coming from a V-Ray scene would be great if we can recognize that and automatically create this effect. So we have deployed this and have run a closed beta with some users that applied for this closed beta period, which is now closed. So we're taking the feedback of that and making some changes, especially to the infrastructure, because also quite challenging to process all of these in a scalable way. So doing it for 1 or 2 assets is fine, but then when people bring gigabytes of assets and not only 1 but thousands, then you need the infrastructure for that, and we're optimizing the cloud workers, etc., to make it cost efficient, and so that we can actually offer this also at a reasonable price to our clients, and that it runs in reasonable time. And of course, we're making constant improvements to the translation itself. And then people can see, once the process is finished, like a real-time model, and also preview the textures, etc. And one thing that also interested us a lot was this automated quality control. So that's something that we actually do when launching 3ds Max, and after having done this conversion process, we render some before and after images. Basically, we re-import the data that we produced and compare to the original, generate this difference image and a score, so that then in the automated batching, people can say, okay, this here looks suspicious, it has a very high error score, so I'll just look into it, and then they see already highlighted, it looks different in these areas, this is where this kind of glass was, and so on. And here you can see another example. So there's this watch model that we created to challenge the pipeline a bit. So it has metalish parts, it has glass, it has things that have an image on it, and also this this pattern on the wristband. And that helped us a bit already to develop a solution for the QA, and also generate things like an HTML report. So if you run it for a huge batch, you get this HTML report. You can look into every single asset in a side-by-side comparison, and ultimately export a CSV file that saves your annotations, so that we just reduce the time that is needed to review these batches. It helps also us to learn. And finally, we are not primarily looking at the cloud customers. That's nice for a trial, but if people want to run that on-premise on their precious data that they want to keep in-house, that's of course another challenge. And in that case, we are building a processing infrastructure for this, so a processing client that allows us to track the status of each asset, etc., while it's being processed. So before before coming to Q&A, I just want to mention one more thing, which is shader graph translation. So it's kind of coming back to the level 3 topic I mentioned, like how to handle complex materials. And one thing that the industry is working on, and actually like one of us is working on a Material X-related hackathon tomorrow, Joao here from our team, is Material X. So Material X is open source, and it's like a framework that allows you to translate between different materials, so people can come and write code that, for example, brings data out of V-Ray by mapping it to a certain schema into some kind of real-time model. And specifically for physically based rendering, when we published RapidPBR and we went to SIGGRAPH, they made this big announcement that was called OpenPBR, and we're like, whoa, what's that? And then we learned that OpenPBR is an initiative where basically Autodesk and Adobe are saying, okay, let's agree on one PBR model, and that should help all of us. So that's really cool. So that's in a nutshell my high-level executive summary of that, and we'll talk more about that during the panel tomorrow as well. And the cool thing is, so you can see here, for example, in the middle, a result of the automated translation of this watch. Admittedly, a bit of apples and oranges because different angles, but overall you can see that the quality on the right-hand side is better than the one in the middle. I think that's pretty clear probably. Look at the wristband, for example. Like, this is what we achieved by just translating the shader graph. And this was done as an experiment. It was done manually, but we just wanted to have a demonstration and say, like, okay, this is where we want to go. So ultimately, if we can take that V-Ray data and translate it to a shader graph, using, let's say, like we provide a USD scene that links to like Material X, material description for this asset, then we have a very solid basis, not only for real-time, but also for offline rendering, and we're basically opening up that box of V-Ray and allowing people to use different renderers for different purposes, leveraging their original data. So with that kind of speed run through RapidPBR, I want to thank you all, and I'm looking forward to your questions.